Hello everyone. So in last class we have seen approximate method of analysis for distribution systems, and there we took a lot of assumptions such as balanced system and uniform loading condition, and we have seen that theoretically we can derive the expressions for voltage drop as well as power loss in general. So the same thing we can end. We are going to extend today, and let us see how these analytical tools can be used for distribution system planning related. So first we will see the concept of substation service area. Substation service area. So it is nothing but the geographical area occupied by geographical land basically, which is electrified by a particular substation. So it area can be of any shape. It is a geographical land, and let us say a substation located at this point. And consider that there is a feeder going. The feeder is not necessarily a straight line. It can take any shape, and so this is the main or primary feeder that I am representing over here. And in this area, there are loads located at different locations, something like this. So in reality, the loads are distributed throughout the geographical area like this. So how the load connects to, or how this individual load connects to this electricity coming from the substation. So the main feeder from this, some laterals are connected. Okay, or laterals are, we can call it as a service lines, and they serve the individual loads. So what are these laterals? Basically, these can be directly connected to the medium voltage level of the feeder voltage level, or there can be a secondary distribution system. For example, when I'm representing this lateral, there can be a transformer which transform the 11 kV to 400 volt, and 400 volt lines, which is basically the secondary distribution system to the individual loads which are there, which are present in this area. So let us say the A, let us say A in kilometer square, that is the cross sectional or the area occupied by that. And let us say total, we know how much total load is there in terms of kVA. Okay, 8 kVA or MVA, basically the apparent power. So now, in order to do the approximate analysis, we need to take some assumptions that since the load is located randomly at some locations, we in order to do the detailed analysis, we can take the detailed exact location loads. But in order to do the approximate analysis, what we can assume is that the load is uniformly distributed throughout the area. So what we can define is some parameter, which is let us say D, which represents the load density. Okay, so load density is basically amount of load in kVA per kilometer square of the area. And now let us assume that load density is uniform throughout this area. That means what are we assuming is there is load at each and every point in this area. Okay, and how much if I take 1 kilometer square of section of this, then amount of load located in that is basically D kV kV A D kV. So we are basically assuming a uniform load density, and with that, let us do the calculations for quantity rest. So typically for distribution system planning, like how the systems are planned is there are several constraints and several factors, but the major factors that we bother about is the voltage drop experienced by the remotest customer, which is located far away from the substation at the towards the end of the feeder. So we are interested in the voltage drop, the maximum voltage drop that appear around the length of the line of the feeder. And the system operator bother about the total power loss happening inside the system. So these are basically two quantities that matter. Uh, while while planning some a new substation or feeder like that. So when we are doing this analysis in this particular video, we are talking about bridge drop and power loss along the length of primary feeder, the main primary feeder, which is this one. We are not talking about the voltage drop and power loss happen through this lateral. So this lateral, which is basically secondary distribution system, we are not planning for that, or we are not taking into account its power loss and voltage drop. So that is a separate thing. It will come when we go for secondary system plan. Okay, so this analysis, the important thing to note is that this analysis is based upon the assumption of uniform load density, and we are doing the planning only for primary system. Okay, going ahead. Now, this load density, this can be, for example, a rural area is there. So there is a lot of space, and there are some homes which are located few distance away from each other, and it is really going to be a long feeder because the homes are located quite away from each other. So in such a case, we can say load density is quite less, right? So electrical load is not densely populated. But in some cities where there is a population is high and residential load is high in the society, or some industrialized area, the load density can be very high. Within a small locality, a lot of population is living and a lot of industries are there. So in that case, load density is very high. So depending upon like whether it is a rural or it is a urban, or whether it is a residential, commercial, or what kind of locality is that, the load density can vary. So typical load density is known prior we take up the planning study. So we assume that the load density in a particular given area is known, as well as the area in kilometer square, that is also known beforehand. So D and A is known. So how much total load is present in the given area? So that will be simply load density, which is in kVA per kilometer square. If you multiply that by total area, kilometer square, that is basically the total amount of kVA power present in that area, and that much power basically the substation is serving. Okay. Now, can we calculate the current taken by substation? So IS, let us assume that VS is the substation voltage, and IS, and assume that this is a three-phase primary distribution system. So current taken by that substation, that can be represented as the total kVA power divided by root 3 times VS. So here we are assuming a balance system and three-phase system. So that's why that root 3 factor is coming. And so we can calculate substation current that way. And substation current, which is required. So that basically defines the how much capacity in terms of current carrying capacity of the substation equipment is required for the given load density and given area. Okay. So using this definition, we can derive the voltage drop and power loss equations. So let us see how to do that. So let us consider substation and feeder, and the area which is served can have some random shape like that. And this is the substation current, which is uh, basically feeding to that total area, and Vs is the substation voltage. Okay. And let us assume the length of feeder is L. Okay. So this total length of the feeder is small L. And we are interested in voltage drop and power loss. So let us say, consider at a distance X kilometer away from the substation. So this is the X kilometer distance. So at this distance, let us consider a small incremental feeder section having length dx, very small, dx tending to 0. So in that dx, how much area will be there? So that much area is covered in a small incremental length of the feeder section. Okay. Now we have seen the total substation current. That is okay. So that is the substation current. But how this current divides into per unit area. How much current is present, or how much current is consumed by per unit area. So this current IS is consumed by area A, right? So what is the current density? Similar to we have here the load density in terms of kVA per kilometer square. We can similarly define the tortoise current density, which is ampere per kilometer square by using this. So what we do with this, we simply divide this full current divided by the total area. So that gives us the current density. So in this case, current density is simply given by IS divided by the total area. And that is from the previous equation, and that is simply d by root 3 times PS. And since this area is having uniform loading, so current density is also uniform throughout. So whenever we take a total area, or whether we take a small area like this, the current density is uniform. So in this strip, which is highlighted here, the current density is also the same. Okay. Now, what we are interested in is first of all the voltage drop. Yeah. So voltage drop in this small area is basically the impedance of area. So it's impedance of that feeder section. So let us assume Z is the impedance per kilometer, and if you multiply that by the feeder section length, which is Bx, so that gives us the impedance, total impedance of that feeder section ZTX. When we multiply by that the by the current which is incoming to that, so let us denote by I suffix x, or let us denote that by I of as a function of x. So if you multiply by that I of x, that gives the voltage drop, incremental voltage drop happening through this feeder section, right? And then we are interested in calculating the total voltage drop from the section 0 to x. Then we basically inherit that right, from 0 to length x, that quantity I of x z dx. Now, what is I of x? So what is that I of x? So basically, this current, it serves some load in this area, in this area basically. Okay, so let me denote that part of area by a suffix x. And after serving, the substation current reduces, and the reduced current that is served this incremental section I of x. So what I can write is I as a function of x is basically substation current minus current served in this area. So how much is the current served in this area? That can be calculated by using the definition of current density. So this current density basically defines ampere per kilometer square. So if we multiply this current density by this area AX, that gives the current served. So that is basically d by root 3 Vs, which gives the current density in ampere per kilometer square. Multiply by that by AX, that gives the that gives basically the current served in area. And from using that definition, we can calculate the IX. IS, we know already, IS is basically T times A by root 3 Vs minus, here we have d8 suffix x root 3 Vs. So that gives simply d by root 3 Vs A minus AX. Okay, so that gives the expression for the current. So A total service area, AX is the service area up to length X of the feeder, and we can get the expression for the current which is incoming to that incremental area dx by using this expression, and we can calculate the voltage drop angle. Now, once we get current, similarly, can calculate the power loss also. So power loss in the incremental section, that is basically 3 I square in R. So R is basically ohm per kilometer. If you multiply with that by the feeder section length dx, that gives the incremental loss in that incremental area. And if we integrate that from length 0 to L, that gives the total power loss. So if you plug in the values of I of x and I of x in the voltage drop equation and power loss equation, we get generalized expression for voltage drop and power loss. So let us do that. So delta V, delta V, it is basically 0 to x, and so it is that I of x dx. So let us substitute value d by root 3 ds a minus ax. So that is d by root 3 ds a minus ax into z dx. So we can take the constant terms common outside the integration. So that gives us dz by root 3 ds integration a minus ax 0 to x. And suppose we are interested in finding the voltage drop, total voltage drop towards the end of the feeder section, the index x will be equal to length of the feeder, because that will be the maximum power voltage drop. Similarly, the power loss can also be calculated as integration from 0 to L. So that gives total power loss. So that is 3 I square R dx. So that is 3 I square is basically d square by 3 ds square a minus ax square r dx. So in this case, root 3 square is 3, that goes out with this, and what we get is d square r divided by ds square integration 0 to L a minus ax square dx. Okay, so that is the thing. Now, for any general service area, we can have the calculation voltage drop and power loss, so like this. Now, let us take one particular example, example of a rectangular service area. So this definite that I am talking about, for example, rectangular service area, what is that? Basically, here we have a substation and the feeder, and that serves this much area. Let us say the length of the feeder or the length of the area, which is same, is L, and the width, height, whatever you want to call, that width is W, and this is the substation, that is current IS, and again, so this is the type of area. So in a well-planned locality or in a particular society or a planned city, service area can take a definite shape like this. Okay. So what is the area of total service area is basically area of the rectangle. In this case, it is L times length times width. Okay. Now, suppose we consider up to length x. So this is up to length x. What is the area a suffix x? That is basically length x multiplied by the width w. And as we have got the expressions for a and ax, we can calculate the voltage drop. So from previous slide, it is dz by root 3 vs. So it is dz by root 3 vs. Those are constant quantities, and integration from 0 to L a minus ax. Okay, that we need to integrate. So it is basically LW minus XW dx. So d shared by root 3 ds, the W will come out as a constant, and what remains inside is L minus X. So its integration is basically L times X minus X square by 2, and we need to put the limit from 0 to L. Okay, so that becomes djw by root 3 ds, and substituting the limits, so that becomes L square minus L square by 2 and minus 0. So simplifying that, simply becomes djw L square by 2 root 3 ds. So that is the total voltage drop that we can obtain. Now, similarly, we can derive the equation for power loss. Let us go ahead and derive it. So, power loss for rectangular service area, that is given by. So, I'm just copying the expression from here and solve the integration. So, that is d square r by v square. Okay, so that is d square r by v s square integration 0 to L a minus ax whole square. So in this case, a is lw minus ax is xw whole square dx. So what we do, let us solve it. So d square r by vs square, we can take w out from this. So that's w square, which is a constant quantity. So w square is outside, and that becomes equal to L minus x square dx. Limit is obviously 0 to L. Okay, so d square r w square the square integration 0 to L. So let us expand that. L square minus 2 Lx plus x square, that is d square r w square by s square. So integration is L square x minus L x square plus x cubed by 3. So I'm carrying out the integration and substitution of the limits. Okay, we do that. D square r w square by s square, so that becomes equal to L cube minus L cube plus L cube divided by 3 minus 0. And finally, the expression that we get is d square r w square L cube divided by 3 s square. So that is the final expression for power loss. Okay. So what is the application of this? Is we can understand that suppose we are planning a substation, and we know what is the length of area, what is the width of. So what we can understand from this is the width, so power loss is proportional to width square and length cube, and voltage drop is proportional to width and square of the length of the feeder. So one of the application can be where to place the substation. So given an area, for example, let us do this case study. So given one cross-sectional area, so this is the area is A, I can place the substation at this point, and I can draw a feeder like this. This is one option. So in this case, the length of the feeder is L, and width is W. Now, another option can be, I can place the substation at the center of this area, and instead of having one feeder, I can now take two feeders out, one in that direction, one in opposite direction. So now the width of that area is still the same W, but now there are two feeders, each having length L by 2 and L by 2. Okay. So now here the voltage drop experienced by the remote test customer, which is this one and this one, that is different than the first case. Similarly, the loss happening in, let us say this is case 1, case 2. So power loss happening in both the cases will be different because now the length of the feeder has changed. So let us see these cases, how to, let us do a comparison in case 1 and case 2. So voltage drop, the maximum voltage drop that is possible in the first case, what we derived just now is basically dz omega L, sorry, dzw L square by 2 root 3 ds. dzw L square by 2 root 3 ds. Now in second case, the voltage drop. So we are bothered about the maximum voltage drop that is happening. And since substation is at the center, the voltage drop will obviously appear at the end of the feeder at their length L by 2. So in this expression, simply we will replace L by L by 2, and that gives dz omega. The other terms will remain as it is. L will be replaced by L by 2, so that comes L square by 4. So multiplied by 1 by 4. So comparatively, you can see in case 2, the voltage drop is reduced by 1/4, which is better. So just by placing the substation at another location, we are able to improve the voltage drop. Similarly, power loss, that is given by d square r w square, d square r w square L cube divided by 3 ds square. Yeah, that is the expression for loss in first case. In second case, similarly, what change will happen is L will be replaced by L by 2. So other terms will remain as it is. And that becomes L cube and multiplied by 1/2 cube, which is 1 by 8. So what is this? This is the power loss in first section. So if we take this figure for feeder 1, power loss is this much. And since we have the two feeders which are like symmetrical or having same characteristic, same power loss will appear in the other feeder also. So we will just multiply that by 2. Okay, so this factor is basically 1 by 4. That means power loss is reduced by 4 times the second case. Then we place the substation at another location. So that is great, right? So in planning study, this is used. Now this is indicating that putting the substation at center point is giving more advantages compared to placing the substation at the corner of the service area. So this is from technical point of view, but there are other non-technical parameters, non-technical factors will also be there. For example, suppose there is a city and at the midpoint of the city there is some building or uh, something which is there that you cannot replace. We cannot destroy that and construct a substation. For example, there can be a forest area or some temple or something, some religious place which cannot be where we cannot build the substation. So there can be physical barriers, there can be right of way issues, and the public safety issues, because since the people are populated towards the center, so there will be issues while placing station at the interior location of the service area. So in this case, we need to do some compromise, obviously. So these are like technical factors, those factors will come. But from technical point of view, if it is feasible, then we can place the substation at the middle. Or we can explore other locations also. We can go for if we cannot place at the middle, then we need to go for some sub-optimal location. Not at the corner, but we can explore. Suppose another location can be here, another location can be here, another location can be here, or anywhere. So that is basically optimization problem. Like which location will give us the minimum voltage drop and minimum power loss. So that is the kind of trade-off we can do. putting the additional constraint and all those things. So basically, this helps in planning substation location. Okay. Now let us go ahead and derive the expression for a triangular service area. So why we are looking at different shapes of the service area is because this is how load is located geometrically, or the uh, areas are planned geometrically. For example, in some planned city, this is the service area. So here we are planning this our substation, and this is the feeder having total length L. Okay, so L is the length, and this is the width. And in the form of a triangle, now the area is there. And let us imagine the same assumptions as we have assumed earlier, which is the uniform load density. So at each and every point within this service area of triangular shape, some load is located. So if D is the load density, and A is the total area, then dA is the total amount of load that is present. So this is what we have assumed earlier. And again, the substation current, which is going to feed this feeder, is given by dA by root 3 Vs, what we have assumed earlier. That is true once again here. Okay. So assuming that the angle subtended by the service area to the feeder, that is theta. This angle is theta. So due to symmetry, this angle is also theta. So this total angle is 2 theta. And from this geometry of the figure, we can say that omega is basically 2 times L tan theta. So this is from the geometry of the figure we can easily see. Now, what is the total area under this, what is total surface area? So it is basically area of the triangle, which is half its half L W. Okay. And substituting W equal to 2 L tan theta, the 2 and 1 by 2 cancel, so that turns out to be L square tan theta. Okay, now again, the same analysis we need to do, consider incremental area dx located at a distance x kilometer away from the substation. And now what is this area, this much area that we have earlier denoted as a suffix x. So a suffix x, it is basically the area served up to the length x of the feeder, which is equal to x square tan theta. Okay. Similarly, you can derive that it is x square tan theta. So once we have A and AX, we can find out the expressions for voltage drop and power loss. So voltage drop, I will just write that equation here. So voltage drop is basically D dz by root 3 Vs integration 0 to L. We are interested in total voltage drop, which is happening A minus AX. So A minus AX, that becomes that is basically L square minus X square, and tan theta we can take outside as a common entity. So tan theta dx. Okay, so we can solve this equation and this integration, and what we get finally, that term I'm writing here. So we get is 2dz whole cube divided by 3 root 3 Vs into tan theta. So that is the final equation we get. Similarly, the power loss, I'm not showing the detailed steps of integration. You can carry out that integration. The power loss, similarly, we can write from the previous slide, is d square r divided by Vs square, and then integration 0 to L. So we need to do is the square of this quantity, A minus AX whole square. So that becomes L square minus XL entire square. And the common quantity which we have taken on, that was tan square theta S. Okay, so if we simplify and solve this, what we get is 8 d square r L to the power 5 divided by 15 v s square multiplied by tan square theta. So this is the expression for power loss. Okay, now we have seen a triangular surface area. Now, what about general area? So the general area can be may not be not necessarily rectangular or triangular, right? And it is not necessary that there is only one feeder coming out of substation. There can be multiple feeders come out of substation, right? So like what we have seen in the previous example here, there are feeders in case two. So suppose there are three feeders, four feeders, and so on, and each is serving some kind of service area. Can we derive a generalized expression? Okay, for n number of feeders coming out of a substation and serving some sort of shape, some sort of a different shape, not necessarily rectangular or triangular. So let us do that. So before going to do that, we'll mention one thumb rule for placing the substation. So historically, it is popularly used. So let us imagine that scenario like there is a substation here, located here, here, and here. So there are three substation light, and they are serving some service areas. Let us say this is the service area. Individual substations are serving approximately. So let's say this is area 1, that is area 2, and this is area 3. So substation located at individual area serving that individual areas. And let us imagine the scenario that now the population of area has increased beyond the capacity of the station. So now the system operator utility is planning to have additional substation, and where to put the station, and what should be the new service area, how the existing load should be distributed among the existing substation and the new substation, how much load should be transferred from existing substation from to the newly commissioned substation. Okay, so that is the decision has to be taken. So the thumb rule is that, when this or wherever these okay, so one thumb rule that the substation should be closest to the load center. Wherever is the load, the substation will be nearest to that. It is obvious because you want to provide the power loss and voltage drop due to long length of feeder, and it is also obvious to understand. So the location of substation has to be such that it maximizes the distance between individual substation and minimizes the distance with uh, uh, individual substation. So what is done typically is that uh, let us uh, let us put the substation here. Okay. So why here? Because it is the boundary point. It is basically the central point, and this is, let us draw the line like this. Okay. So wherever there is an intersection of all three areas, there we will put the substation. And these are the distance. Okay. So where is the service area of this newly constructed substation. So how it is decided, from this yellow line, we draw a perpendicular bisector. So half a length here of this and draw a perpendicular. Okay. Similarly, half a length here and draw a perpendicular. Similarly, half length and draw a perpendicular. So draw perpendicular bisectors and extend that. Okay. So now whatever area is covered in this, that gives the new service area of the newly constructed substation. So it is a thumb rule which is typically followed, and the remaining area goes to the existing substation. So that much yellow highlighted load present in that area, that is going to the new reconstructed substation. So this using perpendicular bisector rule, we can simply follow that. And once again, where to put the substation. Okay, so now once we have the area defined like that, or once we have the area, we can now place the substation here, wherever. That is again an optimization problem. So that is one of the area. Now, since there are three substation, now you can see that the shape of the area looks like a triangle. So this becomes a triangular substation area. What we have seen earlier is triangular substation service area, but substation put at the one of the corners of the triangle. Now, in this case, what we are seeing is triangular service area and substation is put at the center. That is supposed to be the optimal location. Now, how can you find the expression? Okay, so three substation existing, that gives a triangular shape. Similarly, suppose there are four substations existing, that will give a rectangular shape. Similarly, if there is a five substation existing, that will produce a pentagonal shape, or in case of six, we have hexagonal shape, and so on. So we can have any type of polygonal shape taken by the service area. So in those general cases, we can do. So let us imagine a substation, and what I'm drawing is a triangular service area. So we'll draw the triangle like this and this. And let us say that substation is placed at exactly the central location. So, and let us imagine that if there are three such bonds, then substation will serve using three feeders, which is perpendicular to this boundary. This one, and this one. So there are three feeders. Okay. So in this case, what is the expression for voltage drop and power loss that we are going to see? Thirdly, we can have a area like this, and substation placed at here, and perpendicular to that, this is feeder 1. Similarly, this is feeder 2, this is feeder 3, and this is feeder 4. So we can have n equal to 3, n equal to 4, or in case of, let us say, a hexagon. So hexagonal case, 1, 2, 3, 4, 5, 6 substation located at here. So here we will have feeder this 1, 2, 3, 4, 5, 6. Okay, so feeders will be like that. And in each of the cases, you notice one thing: it is the boundary of service area of individual feeder. So notice that this complete triangle is the total service area, but individual feeders does not serve the total area. Individual feeders, let us imagine that individual feeder serves a triangular shaped area like this. So suppose this particular feeder serves this much triangle. Then the next feeder serves the another triangle which is located here, and the remaining feeder serves that particular triangle. Similarly, in n equal to 4 also, we can draw a triangular shape like this, and we can define the feeder's service area as a triangular area like that. In the hexagonal case also, we can draw the boundaries like this, and sorry, forgive my drawing. We can draw a triangular boundary and say that individual feeder is serving a triangular service area. And this we have just derived the equations for voltage drop power loss that we have derived for individual feeder serving a triangular area like this. Okay. Now, in these cases, L is okay. L represents the feeder length. Other quantities are just a constant. What about theta? So in general case, suppose n equal to 4, or it n can be whatever number. In this case, n equal to 6, whatever. So what is theta in each of the cases? So you can notice here that in triangle case, this is the boundary, or boundary of the service area served by the individual feeder. There are three number of feeders in total. So the total angle subtended at the substation, which is basically 360 degree or 2 pi radians, that is divided into three components. So this one, that one, and that one. So this we have defined earlier as 2 theta. So uh, divided by 2 theta. So that 2 pi radians is divided into 2 pi number of, sorry, 2 theta angles, and that gives basically number of service area or number of feeders. So from this we can simply see that theta is equal to pi by n for n number of feeders in arranged in this that symmetrical configuration. So now we can derive the equation for voltage drop and power loss. We can just copy paste this equation. So I'm writing the generalized equation for voltage drop and power loss for substation serving with n number of feeders. So delta V, I'm just writing the expression what was there in the earlier slide. So that is basically 2 times Vj L cube. So what I modify is I will write L suffix n, that represents length of the feeder. Then we have n number of feeders divided by 3 root 3 Vs tan theta, and in this case theta is nothing but pi by n. Okay, I will divide d to dz L cube, then 3 root 3 Vs tan theta. Okay, this is the voltage drop experienced at remotest end. Okay, so this is for individual feeder, and this is also same for all other feeders. Since to symmetry, it is same for all the feeders. So that is the maximum voltage drop that can be seen in this scenario. Similarly, the power loss expression. So it is the same expression, copy paste I will do. So that will be 8 d square r L to the power 5, L suffix n will come there, and divide by 15 p s square into tan square of theta, tan square of pi by n. And in this case, this gives the power loss happening along one feeder. And since we have n number of feeders, the total power loss will be simply multiplied that by n. So that is the expression for power loss. So that is the generalized expression. Okay. By the way, what is the area served by individual feeder? Individual feeder. So last slide here we derived it just. So individual feeder serves the area of L square tan theta. So this case it is basically L suffix n square tan theta. So what I'm writing, what I have to demonstrate is service area of one individual feeder. So that is basically L suffix L square tan theta, which is pi by n. And what is the total service area? Total service area. So this is basically addition of all the service areas of the individual feeders, and that is same as service area of that substation. So since these area are n number of there, and due to 3, it will be simply n times the area covered under individual feeder. So that is n L square tan of pi by n. That is the total service area covered by the substation. Now, what we are interested in is ampacity, or the current carrying capacity. Ampacity is nothing but ampere capacity. So, capacity of feeder. That means how much individual feeder will carry the current, like how much maximum current that is going into the individual feeder. What will be the, according to ampacity, we need to decide the feeder conductor size, its cross-sectional area, and all those things. So how much maximum current can go? It is basically, now we have the service area served by one feeder, which is ln square tan pi by n, and we know the density, the current density, which was how much was that? It is basically d. D is the power density. When we do d divided by root 3 ds, that gives the current density. So current density is basically d by root 3 ds, that is the current density. Multiply that by area. So that is basically ln square tan of pi by n. So that is the ampéricity of individual field. Okay. Similarly, we can derive the current carrying capacity required for the substation of substation. So now substation serves to n number of such feeders. Need to just simply multiply that by number n. So that becomes d by root 3 s n times ln square tan pi by n. So that is the capacity of entire station. Yes. Okay. So now this information is useful in planning the substation and designing the current carrying capacity, designing the location of substation, and according to the area that we are having. Okay. Now here we can also decide the number of given a particular area. We can also decide how many number of feeders we can put into the service so that the area is served. So it depends upon the shape of the area, as well as it depends upon it depends upon like how much power loss we want or how much voltage drop we want. If we increase the number of feeders, obviously what we can say is maybe the if we increase the number of feeders, the voltage drop may increase or decrease, or that we can calculate and do a comparative analysis based upon these particular equations. So let us do a simple case study. Let us do a comparison of number of feeders 4 and number of feeders equal to 6. Okay, and substation is located at the central position. So when we have 4 numbers, we know that the area looks like a rectangular service area, and when we have 6, it is basically a hexagonal service area. Okay, so now we can do a comparative analysis, but just by substituting the values of n equal to 4 and n equal to 6 in the expressions of voltage drop and power loss. And we can see how much voltage drop is happening, what is the ampacity comparison, all those things we can do. Okay, so now let us proceed by before that I need to define the limitations on feeder. Okay, so there are certain limitations with respect to or when we plan for some feeders, distribution feeders. So there are many limitations, but the one of the or the most important or relevant limitations are voltage drop and the other important limitation is thermal loading. Okay, so thermal or temperature depends upon the current carrying capacity. So it's basically also known as ampacity limit. Ampacity is basically ampere capacity, basically the current carrying capacity of the. So what do you mean by this kind of feeder? So when the feeder is voltage drop limited, it is alternate, like in short, it is called as VDL, voltage drop limited feeder. In this case, we cannot design the feeder in such a way that I can not add the extra load on the feeder because the remotest end of the feeder experiences a voltage drop which is not permissible. So the main limit is the voltage drop. In the second case, thermally metered feeder, also known as, it's known in short as TL feeder. We cannot increase the loading on that particular feeder because its current rating is getting exceeded. So every feeder, by in principle, has both these limits. We cannot put additional load because voltage drop will increase and the thermal loading will get exceeded. That will be there. But which one is dominant? Depending upon that, we can classify the feeder as medial feeder or TL feeder. So it can be either voltage drop limited feeder or thermal limited feeder. So let us do this comparative analysis for 4 number of feeders and 6 number of feeders for both the cases in the VDL and TL. So when we have voltage drop feeder, then what is the meaning of that? So when we have 4 number of feeders, we will have some voltage drop. I will denote it by delta V suffix 4. And then similarly, we can have the voltage drop we can obtain when we have 6 number of feeders, so delta V suffix V. So when the feeder is thermally limited, how much maximum load can be transferred through, or how much load can be served, maximum load can be served by this feeders. So the load can be served up to its limit, up to its voltage limit. So let us assume that the feeders in both the cases are operating at up to their maximum capacity, up to such that the voltage drop limit is reached. So in both the cases, let us assume that the upper limit on voltage drop has reached. So that is basically delta V maximum. Since delta V4 and delta V6 is equal, so let us write that in here. So what is delta V expression? Delta V is basically proportional to ln cube tan pi by n. Other are constant. As you can see, other things are constant. So it depends upon n and ln. Okay, so let me write ln cube tan pi by n in both the cases. So since delta V's are different, so it is basically L6 cube tan pi by 6 is same, that is same as L4 cube tan pi by 4. So once we equate that thing, what we get is we can get the ratio of L6 by L4 just by simplifying this expression. So it is L6 by L4 cube we will get tan pi by 4 by tan pi by 6 and take the cube root of that. This we get approximately equal to 1.2009. That value we get here. So what we can see is when we use 6 number of feeders, it can serve the area 20% higher in length. Okay, when we use the 6 number of feeders, that is the information that we got from here. Now we can also compare the service areas, like what is the ratio of service area when we have 6 number of feeders and then we have 4 number of feeders. I'm talking about the service area, total service area. So we have seen in the previous slide here is total service area of the substation is basically n times ln square tan pi by n. So in this it is basically 6 times L6 square tan pi by 6 divided by 4 times L4 square tan pi by 4. And we have the ratio L6 by L4, substitute here and we can calculate it. So that value turns out to be equal to 1.25. That means when we use the 6 number of feeders, 25% extra area can be electrified. So that insight we got from this kind of analysis. Okay, now this is about the this service areas. We can compare the ampacity also, current carrying capacity of individual feeders. So ampacity of individual feeders that we have seen here, so it is proportional to individual feeder capacity is proportional to ln square tan pi by n. So comparison of ampacity. So okay, so let me write ampacity for 6 number of feeders divided by density for 4 number of feeders. So that ratio, that comparison, that can we can also obtain. So it is density of feeder is proportional to ln square tan pi by n. So that is L6 square tan pi by 6 by L4 square tan pi by 6. So that number also we can calculate here. So that number turns out to be 0.8327. So that means there is like this is 0.83. That means 17% reduction in ampacity when we go for higher number of feeders. Right. So this is a comparison what we obtain when we have VDL kind of feeder. So this was the conclusion for VDL feeder. So this slide is for when we have voltage drop limited feeder. Okay, now we can do the same thing when we have a thermally limited feeder, TL feeder. Where what decides whether the feeder is thermally limited or a voltage drop limited? So basically, it depends upon what's the thermal, what is the heat dissipation, what kind of environment the feeders are exposed to. It also depends upon what kind of conductor material, conductor size we are going to use. Okay, so all these factors, these are important parameters while planning the feeders and substation, and we can do the comparison of different number of feeders using the tool we have mentioned over here. So thermally limited feeder. So in this case, the thermal limit is same as ampacity limit of the feeder. So in this case, ampacity of, let me go back, ampacity of the feeder. So in this case, what the thing is, ampacity of feeders is uh, has to be equal to its maximum loading capability, right? So what I'm saying is ampacity of feeder in both the cases of n equal to 6 and n equal to 4 has to be equal, that is equal to the maximum current carrying capacity that we are planning for. So basically we are equating ln square tan pi by n in both the cases for the TL feeder. So for TL, the expression defining equation will be ln square. So n equal to 6, let us take ln square tan pi by 6, that is equal to L4 square tan pi by 4. So this is the main governing expression or the defining expression in this case. Okay, so from this we can get the ratio of L6 by L4. Okay, so that is basically square root of tan pi by 4 by tan pi by 6. Okay, so that thing we can solve, and so that is tan pi by 4 is 1 and tan pi by 6, that is 1 by root 3. So that is basically fourth root of 3. And that's some number we will get there. And what about area served A6 by A4? So area served is basically 6 times this one. So this is 6 by 4. I will rewrite the equation here. 6 by 4 into L6 by L4 square, right? And tan pi by 6 divided by tan pi by 4. So that expression we got here. And so let me write it here. 6 by 4 into L6 by L4 square. So that is basically, that will come out to root 3. Then we have tan pi by 6, which is 1 by root 3 divided by tan pi by 4 is 1. So this cancels out, and 2 is 4 and 2 3s are 3. So 3 by 2, that is 1.5. So as you can see, area served by 6 feeders is 50 times higher than area served by 4 number of feeders when we have thermally limited feeders. and compare this ratio with the previous, where we have only 25% increment when we have voltage drop limited feeder. So this now gives a trade-off. Like for example, suppose we want to serve higher area, then we need to go for thermally limited feeder because it is covering more area in case of n equal to 6. But now we need to make the feeders thermally limited. That means we need to design the thermal insulation. We need to design the cross-sectional area or the thermal properties or the material of the feeder in such a way that becomes thermally limited. Okay, so that guides the design process. So that is when we want the higher area. But suppose we want to save the cost by not putting more material and all into or making the feeder into thermal limited, we can let the feeder voltage drop limited and less area. Suppose we want some less costly solution. So that is design thing. Now similarly, we have seen area coverage. Similarly, we can compare the ampacity of, let me write in short, ampacity for 6 number of feeders divided by ampacity for n equal to 4 number of feeders. So we can write the expression, which is same as earlier. It is L6 by L4 square, 10 pi by 6 by 10 pi by 4. So it is L6 by L4 square, 10 pi by 6 divided by 10 pi by 4. And you can see this is unity. Yeah, this is unity because we started from the same equation. We are writing the same expression again. Ampacity is equal, that means the thermal feeder is thermally limited. Okay, so similarly, we can compare many things. For example, we can compare voltage drop in both the cases. We can compare power loss in both the cases, and these are necessary conclusions. So this helps in the design process. Okay, so that's all for today's lecture. We will stop here.